Morning, everybody. Has everybody gotten the lab pack yet? Okay. For those of you that are in a panic, this is not all of tomorrow's lab. Right? Okay. This has actually, is it 2 labs in it? Yeah. Okay, that's 3 and 4. Lab 4 we're going to do after the exam. Okay. Lab 3 we're going to be doing tomorrow. Apologize that these came to you last minute. But they Xeroxed them for me and then never let me know that they were ready. So I kept waiting for the email saying they were ready. But they never bothered to send it. So that's what happened there. The roll sheet, okay, just again, go through and check stuff off as you go. We'll start it on this side today. You try to make sure that roll sheet gets moved up and down, forward and back, and not sideways unless it's at the back and front. We'll get this right, Oh, I need that unplugged again. And then to hand back labs, okay? These are your lab number 1s. I just put them in these 2 folders, right? One of them says section 1, one of them says section 2. Section 1, when is your time? 8 o'clock. Section 2, 11 a.m., right? And they just go around the rooms again, try to get them to go forward and back as much as possible. Are you doing section 1 or section 2? Section 2 right there. Section 1 on this side. Again, if it's not yours, just pass it back, right? All right. I think we have, that's all the business. When is our exam? Not this week, not next week, the week after, right? Got a little bit of time still. Okay, I'm not talking about any of that. The Physics 4 students have their first exam next week. Yeah, be nice. Be nice. If you run into any of the 4A students, you just tell them they can do it. Yeah, don't laugh at the writing. Don't try. This is what they were doing today. You remember this? Do you remember when you thought this was hard? You were so innocent back then. You weren't all jaded and, brutalized. All right. I made a mistake. It's one of many mistakes I often make, but this one was a little bit big. For some reason, I skipped over this slide, and we didn't do I jumped right into the ring without showing you how to do a straight line first. So I apologize. Let's back up just a little bit, and we'll just warm up our integration muscles for the night. Now that you've got a ring, this is probably going to be pretty easy, right? At least let's hope, okay? So we're going to find the electric field of a straight wire, a rod, something. And the way we're going to set this one up is we're going to drop this rod on the x-axis. We have an origin, and let's say it starts at a position A and has a length L. Total length L, okay? That's what we're going to know. We are finding the electric field, and how are we going to find it? We're going to find the electric field at the origin. So we want to find our point P, our origin point. This is where we want to find that electric field. So what are we going to do to find it? We're going to integrate. We're going to add up a bunch of little contributions. So instead of a rod, we're going to break this rod up into a bunch of point charges. We're going to add up all of those point charges. Now, every single one of those point charges is going to have a different distance, isn't it? But the integral is going to be able to handle that for us. So we just pick, I just like to just kind of go, okay, well, that's the part. This is my little piece of electric field, okay? Then this is the point charge that I'm going to just kind of set up my integral with, and then let the magic of the integral work it all out. So this is going to have a distance x along the x-axis, wherever it is, right? And it's going to be a little tiny piece of charge that causes that electric field at the origin. So now I've got to figure out what my dE is, right? So dE, what is my dE equal? Well, I know that the electric field of a point charge let's do r cubed, r vector is that, right? And I should probably get all my vectors on here. All right, so that's the electric field of a single point charge. And so my little piece of electric field is not a little piece of K. It's not a little piece of R. It's a little piece of the charge, right? The total charge on the rod, I'm going to break up into a bunch of little charges, try and find out what's going on there. So that's that. But now I need my dq, right? What the heck is my dq going to be? So how do I get dq into physical parameters of the rod? Densities. It's this concept and idea of the density. And what kind of density? Linear charge density. So we know lambda is equal to dq over dl or dx in this case. So dq equals lambda dx. And away we go. So I think I've got all the pieces parts here. So I can write down this integral. The integral of dE, which is k dq lambda dx all over. Okay, I didn't do my r vector. What's my r vector look like? It starts where? Where does the r vector always start?
What was the question?
It starts on the thing causing the field and ends where?
On the one being affected.
Where we want to find it. Yes, okay. R vector always starts on the thing that makes what you're looking for and ends where you're trying to find that thing. So in this case, it's electric field. We're looking for electric field. So my R vector is going to start on the charge that's making the electric field I'm trying to find and ends where I'm trying to find it. In this case, it starts on this little piece of charge and goes all the way to the origin. Now, what is the length? What is that distance? It's x. It's variable, right? It's going to change. So that distance is x. And what direction does this r vector point? In the negative x direction. Okay, so what does that mean the magnitude of r is? Not that hard. It's just x. So x cubed. And then my r vector is x times a negative I hat. I need limits. My integral can't really go anywhere unless I give it limits. Where do we want the integral to start? At A. We got to give it where the physical rod is. And where does it end? B, or we can just say L plus A, right? Running along the physical length of the rod. Not starting at the origin, starting at A, and going to L plus A. All right, so now I have math. I can clean this up a little bit. Are there some constants in here?
K, lambda, x.
Yeah, we got a K, we got a lambda, not an X.
Oh, sorry.
We have a negative I hat. What am I left with then? I'm left, this is the part where I always mess up. I'm left with an x dx all over x cubed. Well, okay, so that's, one of those x's cancels with a square, doesn't it? With the cube and becomes a square. So what's the integral of 1 over x squared? No, it's the other way. It's because this is x to the minus 2, isn't it? This is like x to the minus 2 dx. So that's x to the minus 1 divided by negative 1.
Negatives cancel.
Okay, negatives cancel with the I hat in the front, blah, 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 blah. And so, okay, wait a second. So let's just be a little bit more formal here. K lambda negative I is now times 1 over x times a negative 1 evaluated from L plus A to A, right? So this negative sign is going to cancel. And then I'm going to end up with a K lambda I hat times 1 over L plus A minus 1 over A. Just checking to make sure I did all right. Okay, yeah. Okay. So, what does this suggest as to the direction this thing is pointing? Positive I hat. There's a positive I hat sitting in front, right? What direction do we know the electric field should point at the origin if that rod is charged positively? Should be pointing away, right? So we're wrong. We got the direction wrong. Or did we? Which of the two things inside this parentheses is bigger? 1 over L plus A or 1 over A? 1 over A is bigger. Wait, A is a smaller, and you add. It's 1 over it, isn't it? So this negative thing is going to be winning over this. So that would make this whole thing negative, wouldn't it? So then we get the right direction. So yeah, check the properties of your answer before you start jumping to too many conclusions. But that would be the electric field at the origin of a rod along the x-axis. If I gave you a problem, say on the homework or the exam, that is along the y-axis, is it really any different? No, it's just you put y's in for that. Right? So we know we can like store this one in our knowledge bank, right? Like we derived it, we did it in terms of like generic things, so no matter where it starts, where it ends, as long as it's on the axis, and I'm finding it at the origin, I'm golden. What if the point you're trying to find it is on the other end of the rod, somewhere out in space? Now, do you have to redo the whole problem? Yes, because this equation is for the electric field at the origin, right? Not somewhere else. So, you have to do that one again. I'm pretty sure I make you do that one in the homework. All right. Where's the... here's where we left off last time. Remember this one? Where I set up a whole integral that I didn't do? Find the electric field of a ring. Okay. Again, the answer in the box works anywhere along the axis, right? From the center of the ring where we get 0, anywhere along that axis, okay, is going to be golden. Now, we'll get to that and we'll do something. Let's go here, okay? Because we actually want to take the result of this finding of the ring, which is really just kind of a line of charge wrapped around in a circle. And now we want to go to the disk. We're going to find a solid disk of charge, like a vinyl record that's got charge on it or something, right? We're going to find the electric field. And what we're trying to do here, notice, we took you from what was supposed to happen, I was supposed to teach you how to do the line. I'm now done. And then we take that line of charge and we bend it around into a two-dimensional shape, okay? And now we're going to fill that two-dimensional shape in. And what do you think the next step's going to be after that? Make a volume, okay? But we're trying to do all of the basic shapes. Lines, circles, surfaces that are circles, spherical volumes. We'll do some rectangular stuff, right? But that's kind of what we try to develop this basic vocabulary, right? And then we can use that basic vocabulary to build up any shape after that. That's kind of what we're after, okay? So let's do the electric field of a disk. And you're like, let's not, Mr. Balogh. Let's do something else. Okay. These are just stepping stones along the way to mastering how the universe is put together. Okay, let's see. So my disk. Okay, so this is solid now. You know what? Back up. Let's do this again. I'm just going to kind of do this sloppily. I'm going to draw my disk. And then I'm going to draw my axis coming out of the disk. And I'm going to draw like a dot, dot, dot to try and give some idea that this thing is solid. And I could fill that in, right? I could take my pen and try to do a fill or something like that. but it tends to just kind of get messy after a bit. And I think I'm just going to leave it like this, okay? But this disc is solid, right, throughout. It's not empty. I've tried to indicate that here. Okay, similar to kind of what we did with the ring, we want to try to be as clever as possible with our choice of how we're going to integrate this thing. So, what do I mean by that? And this is going to go off the rails, I promise. This is just going to get bad real fast. Okay, the last one, this ring right here, okay, we were able to cheat and we basically set up an integral that didn't vary anywhere and we could just do, DQ and we're done. This one, a little bit. So we want the electric field somewhere in space, along the axis of the ring. Okay? And we're going to find it by adding up contributions of electric field at that point from little parts of this disk. Now there are many ways that we could cut this disk up. We could cut the disk into squares. We could cut the disk into triangles. We could cut the disk into strips. Right? There's lots of different ways to go about it. But we want to do it in a way that avoids having to do double integrals. It takes advantage of things like surface charge density and so on and so forth. So the question is, what is our little piece of electric field? Smaller which way do you think we need to integrate? Yeah, we want to kind of go out along this disk, right? We want to start at the center and kind of go out, right? And so what we're going to do is we're going to take that circle and then bump it out and get a differential area of this thing that then allows us to kind of go outwards like this. So, how are we gonna, effectively, what are we breaking the disk up into if we do it that way? Little rings, right? We already know the electric field for a ring, don't we? We found that last Wednesday. It's right there in the box, right? That's the electric field for a singular ring, right? So can I use that? Yeah, I already did it. I bet your bottom dollar I'm going to use it, right? I've already found it. So if we say that we have the electric field of a ring, right? And that electric field is kx all over x squared plus a squared, okay, to the 3/2 dq. It's kind of just coming, this will be my dE of a ring, right? And my dq, right, is going to have the portion of the charge that is on this disk is encapsulated, right, by this ring and then that little sort of bump out from it. The question becomes, what is the little bump out? How do I get my amount of charge that's on that tiny strip, that green strip that's in there? How do I get that written down in a language that the integral can take hold of? Ooh, we know that we're going to be going out along the radius of this thing, right? Okay. So we've got, oh dear, okay. Do we have an R vector? I mean, what is this x squared plus a squared to the 3/2? What is that? It's an R vector we already developed from this problem, right? And we did have an R vector here because we had a single point charge, right? And it came down put, right? But what we're saying is we're going to find the electric field at point P of a whole ring. So it's not like we kind of have an R vector. So that means that we can use R as the radius of the ring. Just regular radius, not this magical R vector thing. So if I say, okay, this is my R, my radius, okay? And I'm gonna have I know I need a dr, right? We're gonna bump out in the radial direction. What density idea am I gonna reach for? How many dimensions is this? It's 2. So does lambda work? It's area, isn't it? So that means that my dq divided by a dA is going to be sigma. Surface area density. So that means my dq is equal to sigma dA. And now I need to figure out what my dA is. I already kind of know what it is, right? What is the area of that bagel or donut thing that I've cut out of there? Surface area of that circular strip. It's 2 pi r, which is the circumference of one of those rings, times dr. So my dA is going to be 2 pi r dr. I go around one of my circles, and then I bump out in the radial direction. So now I can put this all together. My dA goes in there, my dq goes in there, and my dE goes in there. So the electric field at point P is going to be the integral. This entire mess, kx, and then dq, which is sigma dA, which is 2 pi r dr, all divided by x squared plus a squared to the 3/2 d. Oh, I got my dr there. Let's just double check and make sure I got everything. I have my 2 pi r dr. Yes. I've got my sigma. It came along for the ride. It went up in there, and I left it the kx. Got them. X squared to the 3/2. I got all the parts. Got all the parts. It can be a little bit hairy, right? Now, what are the limits of my integral? So we start at the center of the disk, which is where? It's at 0. And then we go out to what? Whatever the radius of this disk happens to be. I know you guys want numbers, it's too bad. All right. When I wrote down the electric field of that ring, I mean, there's an I hat. We know it's going to be along the x-axis. It was x squared plus a squared, wasn't it? That a tells me the radius of my ring. Is a changing in this problem? What are we calling it in this problem? R. A is not a constant. So I've got to fix this. This is an R squared. This is an R squared. Because I wanted it's all the same to you. I wanted to take that derivative straight out of this thing and ignore that it even existed, right? Because now this integral's become a lot harder, hasn't it? Now, in all honesty, this is probably where you guys are way better at this than I am. I've kind of done the same integrals for 24 years, right? And I don't remember half of the integration methods because most of the integration methods you don't ever use in the real world. Okay? If you got integration by parts down, you're pretty much golden. And if it's not that, then you just go ask Wolfram Alpha. But just as a way to sort of do this integral, Turns out doing it by parts is probably U sub is probably the best way to do this. Okay. So what am I looking at here? So what's constant in this integral here? Yeah, let's clean up a little bit. K x is a constant, isn't it? X isn't changing. X being the distance from there to there, right? That's going to stay consistent. Sigma is definitely a constant. The 2 pi is constant, isn't it? It's all along for the right. What I'm left with is an integral of r dr all over a constant plus r squared to the 3 halves, right? And so if I let u, for lack of a better, let's let it be x squared plus r squared, then what's du going to be? It's going to be 2r, isn't it? dr. I never remember that 2r dr. Okay. Do I have a 2r dr? I have a 2r dr. Right? Okay. I've got it all right there. So this integral looks like kx sigma pi du all over what? U to the 3 halves. And now is that one a little bit more doable? Yeah, right. That feels a little bit better. Okay. So you go and you do that. What do you get? You get kx sigma pi u to the negative 1/2 over negative. Did I do that right? Evaluated from. Let's not change the limits because we're just going to change our symbols back anyway. Okay. Evaluated from the limits. Generic limits. Okay. And then now that I've got that done, can I substitute my u back in? And put my limits back in, and so on and so forth. Okay. So what happens is what I like to call the AMO step. Does anybody know what AMO stands for? A miracle occurred. There's the work. I did it. But I don't want to waste time writing all that down. It would take like 5 minutes, and I got really bad handwriting. So the answer that we get is 2k sigma pi 1 minus x all over x squared plus r squared square rooted. Boom. There's the electric field of a disk on a line drawn through the disk's center axis, right? At some distance x, right? Okay. Yay, hooray. What does that all mean? How do I use this? And what happened? So you understand what happened in the AMO step? I just skipped a bunch of like algebra and cleaning up that integral and doing all that kind of stuff, right? Got it down to its most basic form, or at least as far as physicists would take it. So now we look at this and we go, okay, what does this mean? So first of all, that's magnitude. We know the direction. If it's positively charged, point P will point which way? Away, like along the axis, right? Because of symmetry arguments, there's no other components, and it just points along the x-axis. If it were negatively charged, right, it points the other way. So that's all fine. So this is the magnitude. What's the magnitude trying to tell me? Well, the more surface charge density I have, the more electric field I have. That sounds good. The further away I get, so the bigger x becomes, what happens to the overall magnitude of the electric field? Gets smaller and smaller and smaller, doesn't it? That seems reasonable, right? Is there anything else I can do with that? What would happen? Or something else I can kind of play with. I get some more information out of that. That R, that capital R in that equation right there represents what? The radius of the disk. I made that radius infinitely large? What would the
Electric field.
what's a disk that's got infinite radius? What does that look like? It's a plane, right? It's like a flat tabletop of charge stretching out in every direction, isn't it? So if I better write this down. If R goes to infinity, right? Then what does the electric field equation over there look like? Well, it's equal to 2 times k times sigma times pi times what? X isn't changing. R becomes really big. Really, really big. Like way bigger than X, right? So what is any number divided by an infinitely large number?
0.
It's 0, right? And what's 1 minus 0? Still 1. We just found the electric field of a plane. Not an airplane, but a plane of charge, right? It's 2 times the electric force constant times sigma times pi. There it is. Now, that's not what you're going to see in the book, though. Your book does a little, it's not a trick, it's a definition. It's something I've kind of been hiding from you for a little while, okay? Because it's not that important, but it's going to become more and more important. Our electric field constant is actually, it's not the main constant in Coulomb's law or anything else. The electric field constant K is actually, I know it's 8.99 times 10 to the 9, that's just the number. But it actually is 1 over 4 pi times epsilon naught. I was kind of sloppy right there. Epsilon naught. There we go. Okay. Epsilon naught is a fundamental constant of the universe that we live in. Epsilon naught has a funky name. It's called the permittivity of free space. The naught on there is the free space part. It's basically the value of this constant in a vacuum. Because in 4C, you'll learn about how these constants change in different materials and end up with things like index of refraction and blah, blah, blah. Anyway, it's getting ahead of myself. Epsilon naught, the permittivity in free space, means it's basically a number that sets the strength of the electric field in our universe. It's a fundamental constant in that we can't find epsilon naught. It's not made up of anything else. K is not fundamental. It's just a number, right? But we tend to use it because writing 1 over 4 pi epsilon naught through Coulomb's law and the electric field and all that stuff is just a waste of pencil. Okay? But your book will substitute in for K right here to find the electric field of a plane. And when you do that, you get 2 sigma pi, and then you put in K, which is 1 over 4 pi epsilon naught. And what happens to the pi's? They cancel. What happens to the 4 and the 2? Well, some of it cancels. And you end up with the electric field of a plane being equal to sigma over 2 epsilon naught, which is its most common form that you will see YouTube, internet, books, that sort of thing, right? So just letting you know, right, that if you actually write in what K actually is, you can actually get even simpler forms, right, of what these things are. Now, amazingly, the electric field of a plane, right, so it's got to be infinite, so it's like this tabletop but spreading out in all directions, right? What happens to the electric field the further away you get from the plane? Sigma is just the charge divided by, amount of charge in a certain amount of area? What's 2? It's 2. What's epsilon naught? It's like 2. It's a number. Do any of those things change based on where you are above the plane? How close, how far, any of that? For an infinite plane, the electric field is the same everywhere, no matter how far away you are from it. How many infinite planes of charge do you see? No? What happens if you're trying to find the electric field, say, right outside a car's roof? In a lightning storm? Why would it be important to know the electric field right on the edge of a car's roof in a lightning storm? Where are you safe in a lightning storm? Inside of something that has a metal roof inside, okay? Which is why your car is a safe place to be in a lightning storm. In a tornado, not so much, but in a lightning storm, it's good, okay? Can we calculate the electric field for a given amount of charge per surface area on the roof of your car? Sure. Is your car's roof an infinite plane? No. But if we get close enough, is it effectively infinite for certain distances? You betcha. Right? And then we could even model it better if we had a better understanding of how to do, say, a finite plane. We're not going to do that in here, because as soon as you get away from infinite planes, weird edge effects start happening, and that requires some really hairy mathematics. Okay? Any of you studying Green's theorem, Green's function? They still do that in math?
Yeah.
Is that 6?
It's one of our last topics.
Yeah, okay. And you end up having to like bust it into like different series, and the Taylor series comes back to get you. Then it turns out Bessel functions are a better way to do it. Anyway, it goes back really fast. Okay. The point I'm trying to make here is that at this level we can make sort of some simplifying assumptions. If we get close enough, then it's effectively infinite, and we can calculate these things. Which again, I mean, look at where we started. This looks awful, doesn't it? And yet we made it down to this, right? That's pretty powerful, right? And that's like, what are you going to do if you come up against find the electric field of a disk on your homework? Do you start up there? No, you start in that box, right? You see where you can apply that box. Matter of fact, I think you have a homework assignment, if I remember correctly, where there's like a disk. I think they lay it flat like this, right? And then they like say, well, you cut out like a section of the center or something like that, okay? I think they give you a hint or something. The way you do this problem is you find the electric field at a point P from this solid disk as if the cutout weren't there. And then you add to it another disk at a smaller size with the opposite charge on it. So you can use that equation twice. It's just one of them's got a smaller radius with opposite charge. You add those two electric fields together at that point, and you've got the answer. You don't have to set the problem up again. We've done the disk. Use the disk. We've done the rod. Use the rod. Make sure, though, that when you're doing it, you're applying, apples for apple and orange for orange, right? What do I mean by that? If you've got the electric field on a rod and you're finding it at the origin, the equation I gave you will work. But if you're finding it's not at the origin, now you have to set up and reinvent the wheel, because that's a different situation. It's going to be similar setup and a similar method, but our result is going to be different. One of the things we try to do in physics is develop as many of these solutions as we can, and then use those solutions. Don't keep reinventing the wheel every time. That's called math. Right? We instead go, well, we know what a disk looks like, so can we put disks together to get new disks? And it turns out the answer is yes. Okay? So, trying to help you here, not trying to buffalo you, showing you where these come from, but then letting you saying, well, just use that, right? Now, could that be something that's useful on your cheat sheet for the exam? Right? Find the electric field of a disk. We found it, Mr. Balogh. I just have to plug and chuck. Choo. All right. I'm just kind of rolling through the different geometries here, right? Notice how this one is a bit different from the one we did before. Remember, what we did before was find the electric field at the origin for a rod on an axis. Here, we are going to find the electric field at a point. So this rod, finite length like the last one, but we're going to find the electric field at a point away from the rod on what we call the perpendicular bisector. The bisector means it's cut it in half. Perpendicular means that that line is perpendicular to the rod itself. So at that point P up there, we are going to find the electric field of this rod. That's our goal. How are we going to do that? Where do we start? It's the same place we've always started. You want the electric field? Find the electric field. How are you going to find it? By cutting up all the different electric field contributions from different parts of that rod and adding them all together, right? So the question becomes, what is my little contribution to the electric field at point P? What shape am I going to cut this rod up into? Is it going to be rings? Is it going to be discs? What did we cut the rod up that we started with today? Little point charges, right? Little slices of this rod. So pick one. I'm going to pick, I don't know, this one, right? So that little chunk of my rod right there is going to be my little piece of the electric field. My R vector is going to go from that little chunk, which is sitting at some distance x from the origin, and a distance, I'll call it y, from this point right here. Okay, so do I know my R vector already? Yeah. My R vector is going to be pointing negative xi hat. Okay, where'd the x come from? Distance. What direction is it pointing? To the left, right? R goes to the left and up. And then plus yj hat. So what's the magnitude of R? Square root of x squared plus y squared. All right, cool. Is that becoming just a little bit more reflexive? Okay, hopefully that's something you can kind of like, oh yeah, we got to write an R vector down. What does it look like? Okay, I can find the magnitude. All right, so we know that that's our vector. Why does that all that help us? Well, we are going to take the equation for a point charge, and we're going to, use that, find the use the electric field of a point charge, and then add all those up. But what's my dq going to be? Lambda d x. Which way is the rod going? It's along the x-axis. Okay. And again, that comes from lambda's definition as q over L, dq over dl. I'm getting lazy and writing that stuff down. All right. So let's get this all together. This is going to be k lambda dx all over x squared plus y squared to the 3/2 times a negative xi hat plus a yj hat. And then that goes drunk into this. And I end up with the integral. Do the limits last. K lambda dx all over messy denominator, negative xi hat plus yj hat. Okay. What are the limits? What is x? Where does x start? Where does x end? Well, it starts over here. It ends over there. I can like label the position. So let's see. Let's make that more mathematical. Let's say that this. Let's say that the length of this side is A. So what does that mean the length of the other side is? A. So where does this start? Negative A. And where does it end? Positive A. All right. How many integrals are sitting on the screen? 2. Why is it 2? I have an x component, I have a y component, don't I? Okay. So we're going to separate this out. This is me now doing some math. Okay. So the electric field in the x direction, using that symbology, okay? Magnitude is going to, we'll do all the directions. Okay, so it's going to be negative A to positive A of k lambda dx all over awful denominator times a negative x I hat. And then my electric field in the y direction is going to be a lot of the same stuff. Negative A, k lambda dx, horrible denominator, y j hat. Choose your own adventure. Which one do you want to do first? The correct answer is neither. I don't want to do either of these integrals, Mr. Balogh. I want to change my major now. Like, what has happened? My life was so simple. Pick one. X? Do X first? Okay, let's do X first. No. No, no, don't wanna. So, if I don't wanna, what do I do? Oh! Oh! That's nice. Now, Mr. Bailey, you cheated. Right? Okay? I didn't cheat. I went through all those math classes. I know how to do it. Are you allowed to use this on your exam?
Yeah.
I wish you were. I do. I like. Can we please just use, right? The problem is how do you Wolfram Alpha is on the internet, so I can lock down the browser, but then they don't have enough computers and they don't all work. The logistics of it and the kinds of budgets that we have at this school don't allow us to put you in an environment where I can make sure that the information I'm getting is from you, right? This is you showing me you know what to do, while simultaneously allowing you to use these really good tools. Because, quite frankly, I'm not out to test your ability to do calculus. When I'm looking at a problem and you're doing your exam, and I've seen that you've set it all up correctly, and then the calculus you have a mistake, chances are, if that's the only mistake you made, I might ignore it, even though you get the wrong answer, and go, it's calculus, okay. Right? Okay? Now, to get 100%, do you need to get it? Yes. Right? But I'm willing to give you kind of the majority benefit of the doubt. If you show, I'm your physics teacher, I'm not your math teacher. Right? I want to see that you've done the correct physics. Okay? If you're making the same math mistake over and over again, I might start calling you on it or something, right? Okay, but you miss something somewhere and it has nothing to do with the physics. You come up, you argue it with me, I'd probably give you a point back, right? Okay. So what did I do? I went to Wolfram Alpha. You're not going to have Wolfram Alpha, right? So first of all, spoiler alert. What's the answer? 0. Why is this 0? Well, it turns out that this integral is symmetric. It's even on both sides, okay? So mathematically, even if we did the whole chunk and do a U sub and we'd find out that we get 0 anyway. Wolfram alpha just saved us a bunch of time. We may not recognize that this is a symmetric integral, okay? And we forget that kind of stuff. But how do we know there can't be any x component just by looking at the physics? This side of the rod is going to cause electric field vectors to point away, right? And what's the other side going to do? Also point away. What are the x components going to do? They're going to cancel each other out, right? So we can say, I would allow this completely on exam. You could say, well, Mr. Bailey, this equals 0 because symmetry. You don't even have to use correct grammar. And by symmetry, I understand what you mean, right? The x components are going to cancel each other out. No matter where I go, there's always going to be equal magnitudes, and it's going to go away. I'd be like, yeah, good job. We use this argument all the time in physics. Well, it's symmetric. And we assume everybody knows what we're talking about. All right. That leaves the y direction integral. And unfortunately, this one isn't as nice. And you're still sitting here going, Mr. Balogh, I can't do this on the exam. How am I supposed? So the answer is, I'm going to give you an integral table. You guys ever heard of an integral table? Yeah? Okay. What's an integral table? It's a table of integrals. It's so the one I'm going to give you, this is an older version of Wiley Plus, but it doesn't matter. I'm going to give you the same thing. It's in the appendix of the book. You go to Wiley Course Resources, go to appendix. They have a section on integral calculus in the appendix, and they have an integral table. Okay? And what I've done, number 19 on the table, follows the pattern for the integral that we have. A dx over an x squared and a 3/2 with some constants in it gives me this form, right? So an integral table lets you do is like pattern match, right? Okay? The integral table that I'm going to give you, it's going to be the back page of your exam. Okay? So if you're ever up against an integral and you're like, I don't remember the integral sine squared x dx, it's right there, number 11. Right? I will not make you do an integral on an exam that's not covered on this table. And the good news is there are only 21 entries. Okay? And the first, 3 are kind of stupid, aren't they? Sure. Right? But number 4 is just the pattern for any base, derivative or integral, right? Okay? So even, you probably remember the sine cosine ones, right? I didn't remember the tangent. What the heck is the natural log of the secant of right? But anyway, right? And number 19, this will be what you get. Okay? You guys want to post it to Canvas so you have a copy for yourself? So okay. Post integral. I was going to ask somebody to email me to remind me, so one of 2 things would have happened. Nobody would have emailed me because you all assumed that everybody else was doing it. Or I was going to get 35 emails. Post integral table for B. Do that in 36 minutes. Okay, there we go. All right, I'll remember to do that one because I wrote it down. All right. So, are you okay? Do you understand sort of my expectations for doing integral calculus on your exams? In your homework, go use Wolfram alpha. Just do it, right? Or if you want the challenge, do the integrals. I don't care, right? But don't waste time on it, right? Use the integral table. Use Wolfram alpha. Get your homework done. But on the exam, because I can't give you Wolfram alpha, I'm going to give you this, right? So maybe you might want to practice a little bit with this, right? Reading it, make sure you've got it. And I'll put it on Canvas as a PDF. What's going on there? Okay. So That's the form of the integral. Where were we? We were solving this one over here. Okay, so this EY becomes K lambda y j hat, pulling all the constants out, and then it becomes x all over y squared times x squared plus y squared from negative a to a by Wolfram alpha. Okay, and then okay, clean. Okay. It's just a lot of math there that doesn't need to happen. You can substitute lambda is equal to q over 2a. What, huh? We got a lambda in there, right? But lambda is the total charge on that rod divided by the total length of the rod. What's the total length of the rod? 2a. So putting all that together, I got the electric field in the y direction. Well, let's say the electric field at point P, because we know it's all going to be in the y direction, is kq j hat all over y times the square root of a squared plus y squared. So there is the electric field on an axis that runs through the middle of a charged rod at any distance y from that rod. Right? One of the steps I haven't been doing is checking it. How do you check something like this? Go backwards? Redo the math? No. We want to have an independent way of doing it. One of the ways physicists love to check whether or not something they got is reasonable is by pushing it to its extremes. Are there ways that we can push this function to its extremes? One of the ways that we can do that is by playing around with the length of this rod, which is being captured by this A or 2A thing, right? And one of the big extremes that we can push this to is infinite. What happens if we make this rod infinitely long? That's like one extreme, okay? Or another favorite extreme would be to push the distance that we are from this rod as far away as possible. Let's do that one. So as a check, okay, if y is a lot bigger than the length of this rod, and that the double bigger than just means a whole lot bigger, which in physics parlance means we're effectively making y infinitely big, okay? Then what happens, like what's going on with like the size of A down here and the size of Y? So Y is always going to be a lot bigger than A. So Y is going to be like 100 million and A is going to be 1. We're not going to go all the way to infinity. We're just saying that Y is a whole lot bigger than A. In other words, A doesn't matter. Like, if we get farther and further and further away from this picture, what does it look like the length of the rod is doing? Getting smaller and smaller and smaller until we get to a point where we can't tell if there's any length to that rod. What is it going to look like if it doesn't have any length? It's going to look like a point charge. So that means A doesn't matter, which means the electric field is going to be KQJ all over y times the square root of y squared. What's y times the square root of y squared? It's y squared. What's kq over y squared? It's the same as kq over r squared, right? It's the electric field of a point charge. So, conceptually, we said, okay, let's step away from this rod as far as we can go, right? So that it doesn't look like a rod anymore. We know conceptually it needs to look like a point charge. We did the same thing mathematically, and we got the mathematical form of a point charge? Apparently, this seems to work, right? It follows the functional form that we would expect it to follow if we push it to an extreme. Okay. What about sending it to an infinite point? I need to add page. Add this one. Blank paper. We have kq j hat all over y times square root of a squared plus y squared. We're gonna play around with this just a little bit. Okay. I'm gonna factor out an a squared out of that denominator. kqj all over y square root, and then there's going to be a squared coming out, which means it's going to be 1 plus y squared over a squared. You're like, Mr. Bailey, why are you doing this? That made it worse, didn't it? I'm like, yeah, kind of, but what can I do with that a squared now? I can pull it out of my square root, right? So that it's sitting here in front. Okay. And what is what's Q? What's capital Q up there? It's got to be lambda times the total length of this thing, right? What's the total length? 2a. So if I stick that in there, I'm left with k lambda 2a all over ay square root of 1 plus y squared over a squared, like that. The a's cancel, don't they? Okay. And what happens if I let a become infinitely large? Plus or minus. What's happening to my rod?
It's going further and further out.
It's getting stretched out further and further and further, right? And if I let a go to positive and negative infinity, then what does my thing become? A wire, an infinitely long wire in either direction, right? And now we want to find the electric field of this infinitely long wire. Well, if a goes to infinity, what does this function become? 2k lambda all over y times the square root of what? 1. What happened to the y squared over a squared? It got smaller and smaller and smaller as a got bigger and bigger and bigger, right? 2k lambda over y, and we know that lambda, right? Or sorry, k as a constant is 1 over 4 pi epsilon naught. So that's 2 lambda j hat all over 4 pi epsilon naught for the y, and then I have a lambda all over 2 pi epsilon naught y j hat. What's in the box? That's the electric field of a wire. If the wire's long enough and we're close enough, then we can find the electric field of a charged rod, a charged wire. The charges aren't allowed to go anywhere yet. That's coming up next unit. Okay, right? We start moving charges around. But we've just found the electric field of a wire. And why would we want to know the electric field of a wire? What do wires do? Nothing. Wires do nothing. No, wires do everything. Right? That's what our internet's made of wires. Understanding wires, there's the beginning. I can find the electric field around any wire as long as the charges aren't moving it. Charges start moving, I can do something else. We'll get to, right? But again, we are stepping forward, right? And so now if you're given an infinitely long rod and you want to find the electric field 2 meters away from it, don't do all of this. Do that box. If the rod has length that they give you, do that box. Don't reinvent the wheel. How you doing? This is the big day. This was the day I was like alluding to for the first 2 or 3 weeks of this class. This is like you've seen a lot of integrals today. I'm guessing you probably saw more in math class though, in a single time period, right? But that was just like turning the crank on things, wasn't it? It wasn't like this, where you're like, I don't know what's going on. We've established some patterns today. Take advantage of the patterns, right? Trying to get too far into the weeds. But I did want to see the power of all of that integration stuff that you did learn. And the power of setting up integrals the way that I've been trying to teach you. Okay? You're going to see how this plays out in your homework. I've got time. Do I have time? When's your homework for this chapter due? Is it this coming Monday?
Yeah.
In the last 5 or 6 minutes I've got here, I'm going to, apologies to the ones that have to leave early. I'm going to start this, and we're going to finish it on Wednesday. I'm not going to finish it tomorrow. Tomorrow we're doing this lab that I handed out. Be ready for it. But what I want to do is I want to do the electric field of an arc of charge. An arbitrary section of a rod that has like a circular arc to it. Okay? And so I want to start setting this one up, and we're going to have to finish this on Wednesday. So let's see here. We need a coordinate system. We need our line of charge. We'll do that in, we'll do it in red. So what do I mean? Like, I'm just going to take like an arbitrary line of charge, and that was not good at all. Let's try and make that more of a circle. That stinks equally bad, but we'll go with it. Okay? So what we've got going on here, is we have a beginning and an end to this, and this arc could be anywhere along this axis. We'll call this the x-axis. We'll call this the y-axis. And we've got some angles. So like the arc of charge starts at one point, like one angle, and then it ends at another angle. So like we call these the angles that subtend the arc. We start at one angle, we go to a different angle. And I want to keep this as generic as possible, right? So that we can do any amount of an arc of charge. But like for example, if the arc started at the positive y and went to the negative x-axis and the arc was all in that second quadrant, what angles would we put in? Like 90 to 180, pi over 2 to pi, right? If we had a hema, if it was just like a hema arc, okay, then we would say 0 to 180 or something like that. Okay, so I want to keep this as generic as possible because what I want to do is I want to do the problem once. I want to solve this for every arc of charge I could possibly come up against, right? If I can solve it once, then it's just a matter of get the angles in there that the problem is asking me to have, right? And I start in the same place I've always started, right? With this idea that I've got to break this thing up. And since it's a line of charge, what am I going to break it up into? Little tiny point charges, right? My dE is going to be a k dq over r cubed r vector. My r vector starts on the thing causing the electric field and ends at the point where I'm trying to find it. We are going to find the electric field at the origin, the very center of this arc of charge. Okay. My dq, no surprise, is going to be lambda dl. And now we really kind of have to talk about what this dl is. What direction am I integrating? Is it x? Is it y? Is it both? Yes, it's both, okay? And x and y is actually the worst thing to use. There's something better. And by better, I mean worse. The what? The arc length? The angle? We know it's the angle. We know the angle's changing, right? We know we want to split this up into the d thetas eventually. It's just screaming at us, right? Theta 1 to theta 2 is going to be our limits, and we're going to break this up into... But my dl is going to be r d theta. Where'd that come from? Arc length is r times theta, isn't it? And if we take a change in that arc length, what changed? Is it the radius or is it the angle? It's the angle. So my dl, my ds is r d theta. Nice, okay. And that means my dq is lambda r d theta. And now that means that my dE is k lambda r d theta all over r cubed r vector. What remains to figure out? The r vector. That's where I'm going to leave you hanging. Always leave your audience wanting more. First rule of show business. Okay? But I will leave you at that point. You might want to think about what that R might need to look like. But it does depend on the angle, believe it or not. We'll cover that on Wednesday. I'll see you tomorrow for lab. Read up on lab number 3 there and be ready.